All right, welcome everybody. Hopefully online people can see me and hear me okay. If so, please just let me know in the chat. If, yeah. So as you guys probably know, we are starting or partway through a unit on gases. And in particular, we're talking about air pollution and air pollutants. So we talked a little bit last class, you might remember, about some properties of gases. And a few of those properties include the fact that, first of all, gases take up a far much larger volume than the same amount of substance would as a solid or a liquid. We talked about Charles' law, you might remember, which looked at how temperature impacted gases. We said that at high temperatures, gases expand. At low temperatures, gases contract. And we looked at Boyle's law, which said that as you increase the pressure on a gas, it'll decrease in volume and vice versa. So we talked a little bit about some of those things. So what I wanted to do to start today's class off is show you a little bit of this in action. Okay, so I'm going to just switch my view here for the online folks. I guess you can see me and hear me okay. And I'm going to switch to this view of this container. So hopefully, I guess I'm going to just push this up just a touch so you can see my face just a little bit. This is just a plastic container, which I got a wooden mixing spoon. I'm going to put some liquid nitrogen in this. And liquid nitrogen is nitrogen that's from the air that's been condensed. And liquid nitrogen from the air, you need a huge volume of it to get a relatively small volume of liquid nitrogen. So to give you an idea what that means, if you had 14 grams of nitrogen, liquid nitrogen, which would be just like a little small amount, like, you know, half a shot glass full or so, that would fill a volume, if it evaporated into a gas, of around 22 liters. So it's a huge difference. And so over here, I have a dewar. Can you see that? Yeah, people online can see that fine. So this dewar is the container that we use to store liquid nitrogen. It is essentially a really high-end thermos. It's made out of stainless steel, and then it has inside, it has a second sort of container of stainless steel with a vacuum in between the two layers of stainless steel. And by having this vacuum layer, it makes it really difficult for heat to enter into this container or for heat to leave, you know. So it works like a thermos. If you put something cold inside, it stays cold. If you put something hot inside, it'll stay hot. And liquid nitrogen is at a very low temperature. The temperature of liquid nitrogen in this container right now is around negative 196 degrees Celsius. So, you know, to give you an idea, if you go outside on a day like today, it's probably around 0. The coldest weather probably you may have experienced, maybe, depending on where you've been, maybe minus 40 outside, maybe minus 50 if you've been up somewhere really cold. So this is much, much colder than that, minus 196. And so I'm going to take the top off, and you can kind of see the fog coming off of it. It's so cold, as soon as this cold nitrogen air touches the air that we're breathing right now, it condenses all of the water in the air and turns it into kind of fog. So I've actually never used this container, plastic container, before for liquid nitrogen, so I'm going to hope for the best when we do this. It could crack it, but it does whatever. And I'm going to just pour some in. I wonder what this is going to do. So if you want to look inside, it kind of just looks like boiling water. It's very cold. It's making, of course, this container very cold as well. And the way it kind of behaves is if you kind of have like a hot stove, and let's say you have like a frying pan that's very, very hot, and you pour water onto the hot frying pan. You know how the water will kind of beat up and kind of roll around on the surface. That's effectively what's taking place here. And I'm gonna back this up just a touch. I'm happy it didn't like shatter the bottom out of this, which is fantastic because I was worried that it might. Yet. Let's add some more. If this explodes, no big deal. All right, so what I'm gonna do first of all is, I guess, show to you that this is a liquid. It's just like water, and like water, if you heat it to its boiling point, it's just going to it's going to behave just like boiling water does. So it's really no different. The only difference is the temperature at which this boils is much, much, much colder than what you'd expect to see for ordinary water. So what I have is a kettle. And so this kettle is just an ordinary kettle. It's the type that has the whistle in the end. So typically you fill it with water, you put it on the stove. Once the water begins to boil and converts to steam, steam shoots through the whistle, and then you can tell when the whistle blows that the water is boiled and ready to make your tea. So what I'm going to do is just take this. Hopefully you can see, kind of. What if no, I'm going to move it over here just so. That's a little better, I think. Coming back to this. Okay, so this is our kettle. And what I'm going to do is add some water to the kettle. Not water, liquid nitrogen. Put the lid back on. And what you'll see as soon as I press this, it's boiling right away. So a nice sound there, you know, not too annoying. But you can see this is just like boiling water, except it's boiling nitrogen. And it's just doing the exact same thing, except at a much, much lower temperature. So hopefully you can see this okay. Yeah, you can see that okay on the camera too. And one thing that's interesting, and I don't know if this is going to show up, you can see on the bottom, there's steam coming off the bottom of this, is what it looks like. That's fog, that's water vapor that's in the air right now. We talked about the components of air. We said water can make up to 5% of air. And now you can actually see it coming off like fog. Now, I don't know if you can see that, but does it look like it's dripping? Oh, that's pretty cool, actually. Yeah. Online people, yeah, I can see that too. Maybe? I don't know. I'm guessing. But do you notice there's liquid that's dripping off the bottom here? What do you think that is? Can you see the liquid dripping on the camera? I don't know. So it looks like it's leaking, but it's not leaking. It's made out of metal, stainless steel. It's not going to go through the metal. What about water? Could it be water vapor condensing on this and running off? Well, it's not that either, because this is cold. Water vapor freezes at 0 degrees. And in fact, you can see the sides of this container already turning white. And that's because water from the air is colliding with the surface of the metal. It's freezing, and it's basically creating a layer of frost on the outside. So, you know, with your nail, you could scrape that frost off. Very, very cold. What that liquid is that's pouring off, you can almost see it when it hits the table too, that's air. So air is actually condensing on the bottom of this and then pouring off. It's that cold, right? And so the air is a mixture of oxygen and nitrogen, and that's dripping and running away down on the bottom, just like you see there. Okay. So what I'm going to do is I have gotten some balloons here. Actually, before I do the balloons, I'm going to do one more thing. This is a piece of rubber hose, rubber tubing. just a piece of rubber with a hole in the middle. You know, it's like a hose. It's flexible, it's stretchy. It's just like any piece of rubber you're probably used to. Remember last week I talked about how if you go drive cars sometimes in very, very cold locations, you can have the tires themselves contract a little bit, become flat on the bottom, and the rubber in the tire actually becomes hard. It becomes harder than it would be like what we're used to a rubber tire looking like. So what I'm going to do is stick this in the liquid nitrogen here, pour this into, and really what I want to do is just freeze this to the temperature of liquid nitrogen. And I want to show you how the properties of this stuff can change. What I'm going to do is just move the camera so you can see what that looks like inside. So it's just kind of sitting in there. It's much, much warmer than the liquid itself. So as soon as I stick it in there, the liquid that's in contact with this hose is boiling. I'd say it's almost there. It's getting pretty cold. So now it's quite cold. You can hear that change in sound. It's like hard as a rock, basically. And I've done it before where I hit it so hard it shatters. You don't think of rubber as being something that might shatter if you hit it very hard, but it definitely will. Problem is it sends little like ultra cold projectiles flying through the room, which I don't want to take anybody's eyes out, but other than that, it can be fun. Also, you might notice it's starting to turn white. That's just air, water, vapor from the air condensing on the outside and then instantly freezing to make frost. So it's, I guess you'd call that process deposition when it goes directly from the gas phase to the solid phase. And when you get frost on your windshield in the mornings, that's deposition. The reverse process is called sublimation, when you go directly from the solid phase into the gas phase. And that happens in your freezer if you have like a frost-free freezer, which I think any modern fridge or freezer is like that. If you, for example, pour a tray of ice cubes and leave them in there a long time, the ice cubes will like gradually shrink and get smaller and smaller and smaller. What's happening is the water molecules in the ice go into the gas phase directly, and then your freezer actually pulls that water out of the air, which makes it continue to undergo sublimation. So it's a very slow process, but it can definitely happen. Now, I have some balloons. Balloons are, you know, obviously they're flexible. They're made out of rubber. They're made out of a material similar to this. And what I'm going to do is put rubber balloons filled with air into our bowl here and cool them down to a very low temperature. So if you think about what might happen here, well, the first thing we know is if you cool rubber down, it becomes hard and to some extent brittle. The other thing we know is that if you take gas and cool it down, its volume drops, takes up less space. That's how hot air balloons work, right? You heat up the air in a hot air balloon, it expands, becomes lighter than the surrounding air, and that causes it to lift. So we've got a couple of different things. All right. I noticed as I was blowing up these balloons, the first three were yellow and blue. So I was inadvertently making a statement in favor of Ukraine. So I just kept with the yellow and the blue for now. And I've got a couple of balloons here. There we go. So what I want to do is cool those down just a little bit more. Let's add a little bit more liquid nitrogen. We've got lots. So the first thing you can do is hear them. They sound all kind of crunchy, right? So clearly the properties of the rubber is changing a bit when we get them in here. Secondly, you probably notice that they all kind of shrunk down and they're taking up way less space than they did just a minute ago. And what we can actually do is, once we're kind of sure that they're all cold, they look like they popped. They're all flat. So you can see the balloon, it's just cold. It's obviously deflated, but if you warm this thing up, it just goes back to its original size and shape. So what happens, you cool it down, the air that's inside this balloon just shrinks, it contracts and gets much, much smaller. So I've got some other ones here. Here's a yellow one. You can see it's flat, and you can kind of warm it up. And the air hasn't gone anywhere, it's still in there, it's just taking up a lot less space. It doesn't take long for it to heat back up. Got a few more here. Anyone want one? Want to try? Anybody else? All right. I got one more thing to show you with liquid nitrogen. If you're game, who would like to have liquid nitrogen poured on their hand? All right, come down if you want liquid nitrogen on your hand. Won't hurt, no, it'll be fine. I haven't had very many people end up in the hospital as a result in this class. It's rare. You can come on down. So all I'm going to ask you is show me your hand, open it as wide as you can, and don't make a cup with your hand. Just open it wide. Okay, and just hold it flat, or even at a bit of an angle is even better. All right. I'll use two.
Whoa. Okay.
All set?
Whoa.
See? Doesn't hurt. Who's next? Come on down.
So fun.
It's very fun.
Oh.
All set?
Yep. What? That's so weird.
A little bit got on your shirt there.
That's okay.
Get a bit more here. Spill, spill. Yeah, exactly. There you go. All right. Anybody else? Everyone's good? Everyone got to experience liquid nitrogen on their hands? All right, this looks pretty cool in the video actually. There's like this sea of, well, I guess you can kind of see it from where you are too. This kind of sea of like fog over the top of this thing. There's think we're done with liquid nitrogen. So let's actually, there's one more thing I'm going to do with it. I'm going to move the camera around this way. I'm going to take the rest. So if you're on this side, you may want to come like down here so you can see. We're going to come down the stairs. This is the time it's good to have the wireless mic because I think the people there can still hear me. Come on over. Might be better. No, I'll try this. Is it cold? I should make an entrance like this for every class. So one thing about liquid nitrogen, it's a good thing that we're in a large room, and it's a good thing that the room is also, well, you can see a lot of it sunk in up there. I'm going to switch the view here. And I'm going to say it's, what can happen, because that's a relatively large volume, when that container is full, it'll hold 10 liters of nitrogen. When that vaporizes, it can actually make a large volume of nitrogen in the air. And if you're in a small room, dumping that much could change the oxygen content in the air enough that it could be dangerous. It's not a problem in a room this size. I think I did the calculation once. And also this room has like amazing ventilation. So that reason we should be doubly good. The reason why it didn't hurt when it went on your hand, by the way, is it's the same reason that when you pour water on a hot pan, it doesn't really contact the pan. It kind of bubbles and boils and moves all around. And those bubbles are kind of suspended on a very thin layer of vapor. And that prevents the really cold part from coming into contact with you and really freezing your hand. Of course, if you had a bucket of it and you put your hand in it and set it there, it would freeze it solid. And then if you took your hand out and slapped the counter, your hand would like shatter like glass. And often when I do presentations with liquid nitrogen, especially for kids are like a little bit sadistic, and they always say like, stick your hand in, stick your hand in. And I hear it so many times. Once I actually put on a pair of gloves, and I had one of the fingers, I had a hot dog put in where the finger was. So when I put the glove on, I just kept my finger down, and I stuck the hot dog one in, and then I let it sit there for like 10 seconds, and I pulled it out, and then shattered my hot dog finger. And all the kids started screaming. I was like, no, anyway, it was pretty fun. Yeah, so liquid nitrogen, we have lots of uses for it here. There's a lot of times we might want to keep things very, very cold. We use it for trapping gases. You know, if something's giving off gases we don't want to go into the atmosphere, we can freeze them before they come out and then dispose of them safely. Certain pieces of equipment work better at low temperatures. Certain chemical reactions are so fast that we need to cool them down to very low temperatures to make the rate reasonable. So yeah, there's lots of very important reasons why we have liquid nitrogen and we keep liquid nitrogen. It's used a lot in biology too. I think if you freeze something with liquid nitrogen, like a tissue sample, it makes it really easy to grind into a powder. So I think biologists use it if they want to sort of release the contents of cells or something like that. So maybe there's some biologists in the crowd that can tell me if that's true or not. Oh, okay, so if you freeze cells and then rethaw them, are they? Oh, okay, cool, yeah. So yeah, biologists use it. Physicists certainly do. Chemists, we like liquid nitrogen too. And yeah, lots of fun we can have with it. All right, why don't we get back to actual business today? And we are talking about the pollutants, right? We talked about the first one last class, and the first one we talked about was carbon monoxide. And I took away all feeling of wonder and amazement at haunted houses by telling you that it was probably just examples of carbon monoxide poisoning. I'll recommend to everyone who's hearing me right now, if you live somewhere that has open source, like sources of combustion in the home, like a wood stove or gas furnace or anything like that, it's probably going to be worth your while to get a carbon monoxide detector. I have a friend on Facebook who left her house and took her kids to the hospital on the weekend because her carbon monoxide detector went off and said there was twice as much in the air as there should be. So it's better to get that warning beforehand than find out the hard way. The second one we're going to be looking at is sulfur dioxide. And in this story of air pollution that we're going to be, I guess, looking at in the next couple of days, the thing I really like about these units is that there's hope kind of in it. And when I say hope, what I mean is there have been very serious environmental disasters or issues that are global in nature and global in scale that governments managed to come together on and solve. And the problem of sulfur dioxide is one of these. Sulfur dioxide is a gas that is produced when you take sulfur or sulfur-containing molecules and burn them in air. And sulfur becomes SO2, it's a gas, and it goes into the atmosphere. It can be oxidized further in the atmosphere to SO3 gas, and SO3 gas is quite short-lived. It'll react with water in the air to make H2SO4. Who knows what H2SO4 is? Yeah, that's sulfuric acid. So, you know, if you want to memorize that, there's a nice rhyme. It goes, little Johnny took a drink, but he will drink no more. For what he thought was H2O was H2SO4. It's a good one, right? So yeah, H2SO4 then is up in the atmosphere. It comes down in the rain, and it turns the rain acidic, and it creates something we call acid rain. Acid rain was a major problem in this part of the world back probably in the 1980s into the 1990s before we figured it out. Now, why would you burn sulfur or sulfur-containing materials? The reason is that sulfur is naturally found in many fuels that we normally burn, including oil and including especially coal. And in Nova Scotia, we still burn a significant amount of coal to produce our electricity. And whenever we burn it, all of the sulfur that's in there just gets burned too, goes up the stack, comes out in and becomes acid rain. And the acid rain will come down, of course, and it can acidify lakes and streams, which is hard on anything living in there, like amphibians and fish and so on. It can demineralize soil, so it causes certain minerals to dissolve easily out of soil and makes the soil a lot more barren, harder to support plant life. And so it's really sort of an huge environmental problem. So in the United States, emissions of SO2 have been monitored for a long time, and they peaked around 1970. And up until 1970, and we're going to talk a little bit more about sort of the US environmental movement as we go through the course, but I'd say it was like up to 1970, it was like anything goes. Nobody cared. Like people would just dump stuff in rivers, and there was very little public awareness for sure of environmental problems, and particularly large scale environmental problems. It was sort of like, you know, the world is big, sky's big, the ocean's big. If you pour crap in the river, it just takes it away, and you don't have to think about it anymore. But around 1970, probably starting in the early 60s actually, the impact of a lot of our activity on the environment was really starting to reach public awareness, and legislation sort of followed. So 1970 was the peak. You can see it's dropped precipitously since 1970. There's a map here of the US where it shows in 1995 what the SO2 emissions were. And then just like 9 years later, 10 years later, in 2004, you can see a dramatic decrease in the amounts of SO2. The scale, the color scale here is the same in both. What you'll also notice is that the regions of the United States where the most SO2 is emitted kind of corresponds to the regions of the United States with the greatest population density and the greatest density of industry. So where a lot of the energy is being created and used and being formed. All right. This is a similar picture. It's just showing Canada from 1990 to 2010. So you can see by 2010, it's like kind of cleaned up. And so this is a problem which, you know, used to be a huge, huge problem, and it's probably something you may never have heard of, or at least never heard of as like a current issue. Because, yeah, we kind of fixed the problem. Well, how do we do this? Well, the way I see it, whenever you have a large-scale environmental problem like this, I always see there's 3 necessary steps in order to solve the problem. The first problem is a problem for scientists, and it's identifying the problem, pointing out what the problem is, what's causing the problem. The second step is coming up with a solution, either a replacement for something that's polluting or a technology that prevents it from getting into the environment or something like that. That's step 2. Step 3, which is the critical step, is political change. So having politicians actually force companies to behave in an environmentally responsible way by imposing emission standards or things like this. And you see these have been sort of gradually and progressively pushed in for all sorts of different technologies as time goes on. You know, we talk about cars being really bad for the environment and giving out a lot of CO2, which is true, but compare a modern car to a 1970s car. Like, it's so much better and cleaner. So these were emissions in the UK. They dropped just the same as well. A lot of other countries were able to drop their levels quickly, and by doing this, they employed a technology called scrubbing. So what scrubbing does, it's when you have a power plant, say, that burns coal, and you have this, it's called flue gas, you have this you know, exhaust coming out, it contains the SO2. What you do is you take that gas and you run it through something called a scrubber. And basically what this looks like is it's a container. You can see there's a spray tower there, and there's these sort of nozzles that produce a mist. And the liquid that's being sprayed is a mixture of calcium hydroxide and water. Calcium hydroxide and water will react with the SO2 in the gas to make CaSO3 and water, and then that can be oxidized into CaSO4 solid, which is also called gypsum. So gypsum is this white solid material that's also, it's used primarily as like a construction material. It's in drywall. It's that white powdery stuff in gyprock. The gyp actually stands for gypsum. That's just calcium sulfate. And calcium sulfate can be mined for that purpose, but it turns out we produce a lot of calcium sulfate from power plants from this scrubber process. So not only does it clean the sulfur out of the air, it also produces a usable product at the end. So all you got to do is take these scrubbers, install one on every tower, on every power plant, and that gets rid of like 99% of the SO2, and problem solved. That works great for a coal power plant. It does not work great for a vehicle. So if you're driving a car and you're burning a lot of sulfur-rich fuels, you can't put a scrubber on your car. You can't economically create something that'll do that. So what they do instead for gasoline is remove the sulfur before you actually put it in your car. There's a process, I think it's called Desulphurization. They remove sulfur from your car engine from your car engine. Remove sulfur from the gas before it goes to the gas station. Same with diesel. SO2 emissions, I guess my data here is like 10 years old, but it's still high in a lot of parts of the world, especially developing countries where they need a lot of power and they need to grow their power capabilities rapidly. So, you know, this is something other countries need to be aware of, is the potential impact this could have on the local environment for years to come. Here in the valley, I mean, we're not heavily populated and we're also not heavily industrialized. However, the way the prevailing winds have always gone, a lot of the acid rain that's produced in the northeastern US will actually carry through the wind up over to Nova Scotia and then fall as acid rain here. So Nova Scotia historically actually has been hit very hard by acid rain, even though it wasn't acid rain that we ourselves were producing, right? So they used to call Nova Scotia the tailpipe of the United States. It's like where all the stuff kind of went. Luckily now, it's very much not a problem anymore. Okay, so we have another question. The issue of sulfur dioxide pollution in North America has largely been addressed using scrubber technology. What do scrubbers do? And the correct answer here is they react SO2 with calcium hydroxide to make gypsum. Okay. All right, we're doing good. The next gas I want to talk about is NO2. NO2, you can see it being formed in this reaction right here. This is one that I would love to do in person too, except that gas is kind of poisonous, and I obviously don't want to release a bunch of that into this room right now. So you're going to have to make do with this little video clip. What's going on here? There's a container, a flask filled with, well, it's got some nitric acid in the bottom. And nitric acid will react if you drop a piece of copper in there, and the copper could just be like a penny. And it does this reaction that you see written at the top of the screen where it makes this substance copper nitrate, which is green. Notice in this case, the water at the bottom, the liquid at the bottom, it's hard to see now, but as soon as the penny is dropped in, or as soon as the copper is dropped in, it turns bright green for a minute, and then it gets very, very dark. So just watch at the bottom. See how it goes green first? That's this copper, dissolved copper compound that's in there. But it produces NO2, which is this orangish gas which flies out the top. So this is an important environmental pollutant. And it's formed whenever you expose nitrogen gas to oxygen gas under heat and pressure. So nitrogen gas is in our air, so is oxygen gas. Imagine what's going on in your vehicle's engine. There's a lot of heat, there's a lot of pressure, and there's nitrogen and there's oxygen. That's sort of the perfect conditions to produce NO2 gas. And NO2 gas can get into the environment, react with water, and make nitric acid, which contributes to acid rain. But that's not the major problem. The other thing that it does is it can react with sunlight. It absorbs light, which is why it looks orange. And it creates something we'll talk about later in the course called ground level ozone or tropospheric ozone. So it's really bad for people with respiratory issues. It can cause damage to your lungs. And that's why this one in particular is a problem. This compound, when it gets into the atmosphere in high amounts, that's what we call smog. So smog in the air, really, it's just high excuse me, air, gotta stop for a sec. My throat just went dry. Too much smog here, I guess. Okay, so when it gets in the air, it creates smog, and when you're in a smoggy city and you look kind of on the horizon, it almost looks kind of orangish. And what you're seeing is the actual NO2 gas that you can see that's being produced in this particular case right here. This is Santiago in Chile, and this is, depending on the source or the time of year, one of the worst cities in the world. for smog. And the reason here is largely geographical. You can see it's up against the Andes Mountains there. And by being close to the Andes Mountains, in certain times of the year, the air mass over the city can kind of get trapped and have trouble kind of exchanging and cleaning itself. And you can build up SO2 from all of the activity below, mainly people driving around. You might remember a few years ago, VW cars were slapped with this big lawsuit because they were cheating on emissions tests. The emissions tests that they were cheating on were tests for how much NO2 they produce. Sometimes we call them NOx gases, but I'm going to call them NO2. So this is Santiago in Chile. This is Toronto. And Toronto, you know, any big city in Ontario, you can get smog warnings at different times of the year, depending on, you know, what the weather's been like, how windy it is, how sunny it's been. And if you get a smog warning, it means it's not safe for people with respiratory issues to spend a lot of time outside, because you're breathing in not necessarily directly the NO2, but the ozone that it's producing in the air. Here's Wolfville. We don't have to worry about smog in Wolfville. We don't have near enough cars. So once again, by almost every measure, Wolfville has like the cleanest air in the world. So you're in a very nice place. We should advertise Wolfville, like move here if you have got respiratory problems. We'll get all the Americans to move up here. So this is the VW scandal. They believe that based on the tests that they cheated on, it created 1 million tons of extra pollution that went into the atmosphere around the world. My dad had one of these cars. He bought one of them, and then it was pretty sweet, the deal I think he got. He got to drive it for like 3 or 4 years before the scandal kind of came out. And then they took his car back, and I think they just gave him back what he paid for it. So it's basically like he got a free brand new car for like 3 or 4 years. There were some other options too, like I don't know, I forget what the options were. But. So unlike SO2, NO2 has not been solved. It's been improved in the world, but not solved. That's because you can't put a scrubber on every car. Scrubber technology doesn't work for NO2 gas like it works for SO2 gas. If you look at this world map, this is again a little bit dated now, but what you can see is that basically the regions where the levels are the highest matches up with where the greatest population density is. So obviously, you know, in China on the eastern coast, quite a bit in India, a lot in Europe, a lot on the eastern seaboard of the US. And regions like where there's very few people, like in the Sahara Desert, you see almost none of this stuff. Nova Scotia, we're not so bad, okay? So levels are coming down a bit. Like if you look from the 90s till today, it's probably a little less than half. So it's improving slowly. Most of this improvement is due to improvements in vehicles, actually. Cars being forced to meet emission standards by having things like catalytic converters, by having cleaner fuels, by kind of properly mixing oxygen and gas mixtures, which was not always done. So having oxygen sensors and things like that. Cars technology has improved, which is dropping these levels a little bit, but definitely not eliminating them. All right, what pollutant is an orange gas and is primarily responsible for smog? This is an easy one when you like just finished the unit. Of course, by the time you get to the exam, there's going to be a lot of questions on a lot of little things. So just hope you can keep track of everything. Answer here is NO2. All right. Modern gas-powered cars produce much less air pollution than older ones due to the addition of what feature? And the answer there is catalytic converters. It doesn't do a whole lot for the NO2, but it does definitely take out the carbon monoxide, and it can take out unburned hydrocarbons as well. Or if you get an electric car, it doesn't have any of these emissions. Just think, like electric cars, if batteries could be made cheaper, like they don't have a motor, they don't have a combustion engine, they don't have a muffler, catalytic converter, gas tank, like half the parts of your car don't need to even exist in an electric car. So that means there's lots of work for chemists developing new battery materials. All right, the next gas, I guess, that I'm going to talk about, it's technically not a gas. It's technically a suspension in air, suspension of solid particles in air. And this is just generally, I'm going to refer to it as smoke. And obviously, like smoking cigarettes is one very direct way to get smoke into your body. Here's a don't smoke ad I saw. It said 4,800 different chemicals, 400 toxic, 40 carcinogenic. I just want to say that this kind of complaining about smoke for this reason goes against what I told you in the first couple of units, which is the number of chemicals is irrelevant. What matters is the dose and the frequency. Now, typically, for smokers, the dose is also high enough to cause a lot of damage. So I'm not obviously trying to say that smoking is like harmless. But this is an ad that's capitalizing on sort of the public's willingness to, or lack of willingness to think about deeper issues like dose and like, you know, chronic versus toxic and all these sorts of things. They just say toxic. But yeah, smoke is definitely bad for you. It's been interesting for me over my lifetime to see how the public perception has changed of smoking. Now this is older than me, this ad, but it's like more doctors smoke Camels than any other cigarette, kind of implying that it's healthy. This was another one, blow smoke in her face and she'll follow you anywhere. Like, this is not the modern conception of cigarette smoking. I would probably say if I smoked a cigarette and blew the smoke in someone's face, that would be taken as an insult, not as a, I don't know, like an attractive thing. I guess what I think is when I was a kid, I'm going to use Tim Hortons as my meter stick here. Because when I was a kid, like Tim Hortons, everyone just smoked at tables in Tim Hortons. You walk in, get your food, walk out, get your coffee, whatever. And to me, I just never really thought about it. You just took it for granted that you're going into a restaurant, it's going to be filled with smoke, and that was just that. Then I remember, because I grew up in Antigonish, at some point when I was a kid, they built a second Tim Hortons in Antigonish. One was smoking and one was non-smoking. And actually, so if you were out like at a soccer game or something and somebody brought Timbits, you could eat the Timbits and you could tell which one they came from. Because if they came from the smoking one, you could taste the like smoke in the Timbit. And if it came from the non-smoking one, they didn't have that taste. Then it changed so that the smoking Tim Hortons had like a smoking section. And the smoking section was like walled off with plexiglass. And you could it just looked like people were hotboxing in there, like it was just, you know. And then slowly that disappeared, and then people, if they were smoking, they had to stand outside. Then it went from there, if you were standing outside, you'd have to go to the sidewalk. You couldn't stand in the parking lot or close to the door. So it's just slowly, you know, pushing smokers to the edges. When I was an undergrad, I remember like you go to bars, you know, like the pub is the Antigonish equivalent of Anvil. And in restaurants and bars, when I was an undergrad, which was like late 90s, you could not smoke in restaurants, but you could after 9 p.m. So the bars, like, they'd fill up with smoke starting at 9 p.m. It was weird. And you'd go home and all your clothes just, like, you couldn't put them back on in the morning. Not that you'd want to anyway, but that you could definitely smell if someone had been out or not. That's certainly not allowed anymore. I don't think you can smoke at all. Probably anywhere indoors. I can't imagine a public place indoors that you'd be allowed to smoke. So definitely a lot of change in sort of public awareness of this. This is one. Melissa Williamson, a Bullitt Avenue resident, worries about the effect on her unborn child from the sound of jackhammers. You can see she's smoking a cigarette here. This is another, I guess, it speaks to sort of something I alluded to in the first couple of units, where often people can very easily develop fear and worries about things that aren't really the things they need to be worried about, right? They could be causing themselves direct harm in some very obvious way and worried about some other hypothetical harm which actually isn't really harmful at all. So this is maybe a nice example of that. So why is smoking bad? Well, one of the main reasons smoking is bad is because smoke contains these soot particles that you're breathing in, and we call this stuff particulate matter when it's in air. It doesn't have to be from cigarettes. It can be from all sorts of different things. And we have in our lungs these little structures called alveoli, which I'm probably pronouncing incorrectly. But essentially what they are these little, in your lungs, these little kind of air sacs that when you breathe in, they inflate with air, and it provides much, much greater surface area inside your lungs for oxygen to exchange and oxygenate your blood. So it's a way that your lungs increase surface area to make it so you can bring in more oxygen. What can happen is if you have particulate matter, little particles, solid, insoluble particles that are on the scale of around 2.5 microns. So a micron is like 1/1000th of a millimeter. So these are very, very small particles present in cigarette smoke. They're about the right size to clog up the entrance to these alveoli, which makes it so air can't easily get back and forth and makes it so your lungs have a reduced capacity to extract oxygen from the air. If the particles are smaller than that, they can kind of slip in and out, no problem. Or if they're larger than that, they don't kind of get wedged in there in the first place. But if they're around 2.5 microns, that's sort of the magic bad size that you don't want to be getting in. And you might have seen pictures like this before where you see like a smoker's lung versus a healthy lung. And I say healthy, I mean obviously that person's not very healthy because their lung is in a bag, but you can see the picture on the left here of the black lung. The reason why it's black is because there's tons of little soot particles jammed in, all those little alveoli. And probably if you're a smoker for a long time and you quit, over time your lungs would clear some of this stuff out. But it does a lot of things that are bad. First of all, it creates sort of constant irritation in your lungs. And there's a theory, actually, that one of the possible causes of cancer is chronic irritation. Because if you're chronically irritating, that means it's always healing. And if it's always healing, there's a high metabolism. If there's a high metabolism, there's high cell division, and there's a much greater chance of cancer developing in that area. I don't know how widely accepted that theory is, but I know from a doctor friend that that's one theory of how some cancers can form. The other thing, of course, is it means your lungs just aren't as good at drawing oxygen out of the air. So, you know, if you went for a 10K run, you're probably going to be huffing and puffing a lot more if you're a smoker than if you're not. There's lots of other sources of PM 2.5, particulate matter 2.5 microns. Besides just cigarette smoke, this guy is working in a coal mine. And you can see after he's taken his shirt off how much coal dust has settled on his skin. And he's cleaning himself off here. He's also smoking. I guess he's doing two things at once. But this causes a problem if you work in coal mines a lot and you get a lot of this inhaled powder, this dust. It's a problem that's called black lung, which is very similar to the problem you get from smoking. There's natural sources of particulate matter. This is a volcano. It produces all this ash. It puts a lot of this particulate matter in the air, which obviously can be bad for you. You can see this is fallen on a city, and it's like coated cars, almost like snow, so much of it. Forest fires produce all kinds of smoke, and from time to time here, there'll be like forest fires in Ontario or somewhere, and you'll actually see the smoke migrate to Nova Scotia. So it can put this particulate matter in the air as well. Construction, demolition, destruction. This is the World Trade Center. That produced a lot of particulate matter that went into the air. And there's a lot of people who developed respiratory problems shortly after, particularly first responders. And so, there's lots of different sources of particulate matter. What does PM 2.5 mean? Correct answer here is particulate matter 2.5 microns in size. Great. We are at 1:55. We're doing just great for time. Why is it a health concern? It obstructs alveoli in the lungs, negatively affecting respiration. Okay? So that's the main issue. Here's a map of Canada showing particulate matter levels. Particulate matter is one of these things that Environment Canada monitors. What you might notice is it's sort of high in populated areas like Vancouver, Calgary, Edmonton. You see Winnipeg's kind of high. Of course, Ottawa, Montreal, Toronto, all along there. And Halifax gets a little red dot too for particulate matter. So it seems the particulate matter in Canada is highest where there's the most population, most activity. And this is probably from things like, you are burning wood in a wood stove and that puts smoke out to the air in the chimney. Some people in some places burn garbage outside or burn brush, or your house catches on fire or whatever. Industry can put all sorts of particulate matter in the air as well. Another one up here. What's that? I think that's Fort McMurray. Is it? Yeah. That's, of course, oil sands, where there's all kinds of industrial activity going on up there. So that's pretty high as well. So, it's kind of what you'd expect in Canada. Particulate matter has been dropping in Canada, though, and this is, kind of a result of new restrictions on industry. The fine particulate matter, it's dropped a little bit, maybe from like 400 to 300, but, it's not a problem that's gone. This is still 2010. I need to get a 2020 map here just to update this data a little bit. But here's a picture map of the world looking at particulate matter. And this is where you're going to look at it and say, oh, we're fine here in Canada. Look, the whole country is like at the lowest level. And look where it's high. There's this sort of corridor through here where it's very high. Really, if you're in Canada, particulate matter is not going to be much of an issue. Now, we talked about where it comes from. It's from burning things. Anything that creates smoke or dust or whatever contributes to this issue. And, you expect maybe high levels in a place like China or India, where there's a lot of people living there and that have a lot of fires for food, cooking, heating, whatever. But look at Northern Africa. Northern Africa has very low population density and very low density of like industrialization. Why do you think it's so high all the way through there? Any guesses? So that could probably help. Yeah. Yeah. So just for people who didn't hear that online, there was a suggestion that maybe it's where other countries might send garbage to dispose of or burn or whatever. It's actually not that either. The reason is, that whole region of Africa, that's where the Sahara Desert is. And when it gets windy, the dirt, the dust, the sand gets airborne. And so that particulate matter that you're finding there is just like airborne sand. Perfectly natural, nothing to do with human activity at all. I saw a documentary once, and it was talking about how airborne dirt and sand and so on from Africa travels here, this way, and deposits in the rainforest. And apparently it brings, I don't know, it brings some nutrients or something, some elements that plants there need to thrive. So part of the reason why there's so much, diversity of life and density of life in Brazil, like near the Amazon, is this sort of constant supply of fertilizer that's blowing across the ocean. So, yeah, we're good up here. Okay, we're going to look at another gas here, which this actually is a gas. It's VOCs, which stands for volatile organic compounds. Volatile has a different meaning in chemistry than we would use it for in regular everyday speech. If you said your friend was volatile, probably what you would mean by that is that your friend easily flies off the handle, they get a short temper, they explode easily. And if you think about a chemical being volatile, maybe it's like explosive or touch sensitive, shock sensitive, or something like that. That's not what we mean when we say a chemical is volatile. What we mean when we say it's volatile, it just evaporates easily. And probably, I would say anything is volatile if it evaporates more easily than water. So gasoline is a volatile organic chemical because it evaporates easily. Alcohol, ethanol is, you know, when you rub it on your arm to get a needle, it feels cold, it evaporates quickly. Isopropanol, all these things are volatile organic compounds. There's natural sources and man-made sources as well. Biggest one is from transportation, which would be like unburned gasoline. Other things, solvent use. So if you're using solvent-based oil paints, or for example, like turpentine to clean your brushes, or there's all these organic chemicals. Nail polish is another one, nail polish remover, puts volatile organic chemicals in the air. And there's some other ones here as well. Canada, in terms of kilograms per person, is super high for VOC emissions compared to most other European countries, for example. Well, I know we're not European here, but you know what I mean. The reason why Canada is so high is because of our oil and gas sector. Oil and gas, the extraction of oil and gas ends up putting a lot of volatile organic compounds in the air. Oil and gas industry in Canada, by far, is the #1 source or cause of this. Paints and solvents, #2. So this would be, it could be industrial use, it could be home use. If you're using like a spray can to spray paint something, it's probably got VOCs in it that are going out into the air after you spray paint something. By province, you see Alberta, despite not being the largest province by population, is the #1 province for VOC emissions because that's where the majority of the oil and gas industry is. See Nova Scotia, we're kind of peanuts down here. We don't really do too much for VOCs. If you look at emissions trends in Canada from the 90s to about 2015, sulfur oxides is the blue line, SO2 way down. VOCs, probably next, down quite a bit. Particulate matter, down a little bit. Nitrogen oxides, I guess, down a little bit as well. So, I don't know, there's improvements, but we were never too high to begin with here for any of these things. All right, so these are just, I'm not going to talk about this much. I just want to say that all of these compounds, prime particulate matter, SO2, NO2, ozone, we're coming to next class, are things that are monitored by Environment Canada, and there's regulations about what's allowed to be in the air and air that you are exposed to before it becomes a health concern. So I think in most parts of Canada, this is really not too much of an issue. One thing I do want to tell you about, though, is that many activities that we do can affect the quality of the indoor air that we breathe. And it's actually kind of ironic in a way, because a lot of the things that we do to like clean the air or purify the air actually make it lower quality. So if you, like, I know some people, incense kind of comes in and out as a kind of a trend for people to burn incense in a room to make it smell nice. That's adding a lot of particulate matter into the air. Clearly, like, what you often find is when women get pregnant, a common thing you'd want to do is paint the new room for the baby, like create the nursery and get in there. It actually matters what sorts of paint that you use. If you're pregnant, you don't want to be exposed to high concentrations of certain chemicals. Another one that kind of jumps into my mind is when you buy those vinyl shower curtains, you know, those plasticky, thick plasticky ones, and you open them up and they have a really strong smell. Those are volatile organic chemicals. What I usually do is I just put it in a room on a nice day, open the windows and make sure there's a lot of airflow for the first few days for it to air out. Actually, I use a cloth one. Actually, in my current shower, it's glass doors, so it's not an issue. But here's one. Remember David Avocado Wolf suggested getting one of these to improve your air quality? These don't work either. Last gas. I think this is the last one I want to talk about. And this one, I think is particularly important here in the valley, is radon. And radon is a radioactive gas that is produced naturally underground by the radioactive decay of uranium. And the reason I'm focusing on this one in specific here is because the soil in parts of the valley is actually fairly rich in uranium, which means we probably produce more radon than many other parts of the country. So what happens is you have uranium underground, undergoes radioactive decay, produces radon, and it kind of just percolates upwards from underground into the soil. So if you have a house, right, and you have like, say, cracks in your basement floor, it can work its way up through the cracks, it can find its way in through pipes, it can find its way in through lots of different ways. And it's quite a heavy gas, so typically if it gets into your basement, it'll just sort of sit there. And particularly if it's an old home that doesn't have very good ventilation, that could just build up and build up over the years and reach very high levels. And radon, because it's radioactive, if you're breathing it in, it can damage cells and damage DNA inside your lungs and actually cause lung cancer. Radon is the number 2 gas, sorry, it's the number 2 cause of lung cancer. Number 1 being smoking. Number 2, radon gas. So radon gas is responsible for about 10% of lung cancer cases in North America. Smoking is about 89%. And 1% is sort of like cause unknown. Neither of those two or something else. So this is just showing the radioactive decay. It starts with uranium, slowly breaks down into radon, and yeah. If you have an issue, if you're in an old home, especially if you're in the basement of an old home, and it doesn't have very good ventilation, like most modern builds will have like an air exchange system in the house. Old houses may not. You can get yourself a handy radon detector. And this will measure radioactivity of the air and go off if the radon levels are too high. And if that's the case, you would want to install some sort of air exchange system to prevent radon levels from building up to a high level where it could be dangerous. It's funny, like at the end of the day, I wonder like if does anyone come home from these classes and like buy a radon detector, a carbon monoxide detector, and like I just imagine your wall will, like smoke detectors obviously there, have all these different detectors for all the different things that could go off. There should be like a one detector you get that does all of them. Maybe I should think about that. Detect some things too that like people didn't know they had to worry about. Like things they don't have to worry about, but like it'll detect it anyway, you know? Like it'll detect, I don't know, hexane. Why do I have to worry about that? You don't, but we can make it. All right, what does the word volatile mean in the context of volatile organic compounds? Easily evaporates, catches on fire, easily causes toxic overdose, or easily explodes. Correct answer here is easily evaporates. Good. We're on slide 104. We're cruising through. Which noble gas is radioactive and can increase lung cancer risk? The answer is radon. The rest of them are all noble gases, but radon is the only one there. What's that? That's it. We're done. So we will come back on Thursday. I will have a fulsome description for you on Thursday of assignment number 2. And we will start our next unit, which is air pollution 2, which is going to be looking at ozone, CFCs, and sunlight. Awesome. So goodbye as well to everybody online. Get some good numbers.